More than 15 billion miles from Earth, a spacecraft the size of a small car is dying. Its nuclear power source, the same one that has kept it alive for nearly 50 years, is losing energy faster than engineers had hoped. And in April 2026, NASA made a decision that stopped the space community cold. They turned off one of Voyager 1's last remaining science instruments, not because it stopped working, because the spacecraft is running out of the power needed to keep it alive at all. And what that dying machine has been sending back from the edge of known space before it loses the ability to send anything back at all is changing what scientists thought they knew about the universe beyond our solar system in ways nobody fully anticipated. This is the full story of what Voyager 1 has just revealed, why it matters more than most people realize, and what is being done in a last desperate attempt to keep humanity's most distant ambassador to the universe alive, long enough to finish the job it has been doing for almost 50 years. Start with the scale of where Voyager 1 actually is. Most people have heard that Voyager 1 is the farthest human-made object from Earth. But hearing that fact and understanding it are two entirely different things. As of mid-2026, Voyager 1 is more than 15 billion miles from Earth. That is 15,000 miles. If you could somehow drive a car at highway speed without stopping in a straight line toward Voyager 1, the trip would take roughly 17,000 years. A radio signal traveling at the speed of light takes more than 22 hours to make the one-way trip between Voyager 1 and the antennas of NASA's Deep Space Network on Earth. If you send a command to the spacecraft, you wait 22 hours for it to arrive. Then you wait another 22 hours for the confirmation to come back. A simple question and answer between engineers on the ground and a spacecraft in deep space takes nearly 2 days. By approximately November 13th, 2026, the distance will pass a threshold so psychologically striking that NASA announced it months in advance. On that date, Voyager 1 will be one full light day from Earth. The signal it sends will take exactly 24 hours to arrive. Susie Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, described what that means in human terms with an example that makes the distance visceral. She said that if she sends a command to the spacecraft and says, "Good morning, Voyager 1," at 8 in the morning on a Monday, she will get Voyager 1's response back to her on Wednesday morning at approximately 8 a.m. The command travels at the speed of light for one full day. The response travels at the speed of light for another full day, and yet the spacecraft is still in contact, still sending data, still doing science. That, more than any number of miles, captures what Voyager's survival represents. The mission was designed for 5 years. It has now operated for nearly 50. Launched in September 1977, Voyager 1 completed its primary mission of exploring Jupiter and Saturn by 1980, returning the first detailed close-up images of Jupiter's Great Red Spot, Saturn's ring system, and several of their moons. Scientists used the gravitational pull of those planets to slingshot the spacecraft onto a trajectory that would eventually carry it out of the solar system entirely. Every year since, Voyager 1 has been moving away from the Sun at roughly 38,000 miles per hour, covering more than 900 million miles per year of additional distance. It crossed the termination shock, where the solar wind first begins to slow against the pressure of the interstellar medium in 2004. It crossed the heliopause, the true outer boundary of the solar system where the Sun's influence ends, in August 2012. At that moment, it became the first human-made object in history to enter interstellar space, the vast darkness between the stars that nobody had ever directly sampled before. The data Voyager 1 has sent back from interstellar space has been full of surprises. The interstellar medium, the diffuse plasma, gas, dust, and magnetic fields that fill the space between star systems, was thought to be relatively quiet and uniform. What Voyager 1 found was something different. The density of the interstellar plasma is not constant. It varies. There are pressure fronts, regions of higher density that Voyager 1 detected as it moved through them. There are magnetic field fluctuations that do not match predictions based on models built before any spacecraft had ever actually measured the interstellar environment directly. And there is the plasma hum. Voyager 2's crossing of the heliopause in November 2018, 6 years after Voyager 1, added a crucial second data point. Because the two spacecraft crossed the heliopause in different directions, they entered interstellar space at different locations around the edge of our solar bubble. This meant scientists could compare what the heliosphere looks like from two different vantage points simultaneously. The comparison produced an immediate surprise. The heliosphere is not symmetric. It is not a uniform sphere expanding equally in all directions. The heliopause that Voyager 2 crossed was at approximately 119 astronomical units from the Sun, slightly closer than the 122 astronomical unit boundary that Voyager 1 had measured. The asymmetry suggests that the interstellar medium is pushing harder on one side of the heliosphere than the other, compressing it in that direction. Determining exactly why and modeling the full three-dimensional shape of the heliosphere based on data from 2 spacecraft that crossed its boundary in different places is an active area of research that the Voyager data made possible, and that IMAP and future missions are now trying to refine. The plasma hum is one of the most remarkable and least discussed discoveries of the Voyager extended mission. Voyager 1's Plasma Wave System, one of the instruments that is still operating as of April 2026, detected a faint, continuous oscillation in the charged particles of interstellar space beginning in 2017. Unlike the discrete, event-driven signals that the instrument had detected before, this hum is persistent. It does not spike during specific events and then quiet down. It is always there, a constant low-frequency vibration in the plasma of interstellar space that scientists did not predict and do not yet fully understand. Stella Koch-Ocker, a researcher at Caltech who led the analysis of this phenomenon, described it as a very weak but persistent signature that tells us the interstellars. Medium is more active and more structured at the scales Voyager can probe than our models suggested. It is, in a very real sense, the universe humming, and Voyager 1 is the only instrument we have ever built that is in a position to hear it. The plasma hum is not the only mystery Voyager 1 has uncovered in interstellar space. The boundary between the heliosphere and the interstellar medium, the heliopause that Voyager 1 crossed in 2012, turned out to be much more complex than a simple sharp edge. The heliosphere does not end cleanly. It ends in a turbulent, patchy transition zone that Voyager 1 took years to fully exit, during which it detected multiple partial crossings back and forth across the boundary as the heliopause itself shifted position in response to changes in solar activity. Models of the outer heliosphere had treated the boundary as relatively stable. The data showed it moves and breathes with the 11-year solar cycle in ways that the models had not captured. The entire outer boundary of our solar system is more dynamic, more variable, and more responsive to the sun's rhythms than anyone had anticipated. There is also the ongoing mystery of what physicists call the interstellar magnetic field direction. Before Voyager 1 crossed the heliopause, measurements of energetic neutral atoms and other remote diagnostics suggested that the interstellar magnetic field just outside the heliosphere was oriented in a specific direction. When Voyager 1 actually measured the field after crossing into interstellar space, the direction it found was different from the predictions. The discrepancy has been studied carefully and remains an active area of research. It suggests that either the local interstellar magnetic field is significantly influenced by the presence of the heliosphere itself in ways the models do not capture, or that our remote sensing techniques for measuring magnetic fields at interstellar distances were introducing systematic errors. Either possibility has implications for how well we actually understand the structure of the interstellar medium through which our solar system is currently traveling. All of this remarkable science is now under existential threat from the most mundane of engineering realities. The 3 radioisotope thermoelectric generators that power Voyager 1 were loaded with plutonium-238 at launch in 1977. At that time, they produced approximately 470 watts of electrical power. Plutonium-238 decays with a half-life of 87.7 years, which means it loses roughly half of its radioactive heat output every 87.7 years. After nearly 49 years of operation, the RTGs are producing less than half their original output. The exact figure as of April 2026 is below 270 watts and declining by approximately 4 watts per year. As the power output falls, engineers face increasingly difficult choices about what to keep running and what to sacrifice. The process of shutting down Voyager 1's instruments began back in 1980 when the photopolarimeter system was turned off due to degraded performance. Since then, instruments have been switched off one by one. The cosmic ray subsystem on Voyager 1 was shut down in February 2025. Before that, the imaging cameras, the ultraviolet spectrometer, and several other instruments had already gone dark over the decades. On April 17, 2026, engineers at NASA's Jet Propulsion Laboratory in Southern California sent commands to shut down the Low Energy Charged Particles Experiment, or LECP. The LECP had been operating almost without interruption since the moment Voyager 1 launched in 1977, nearly 49 continuous years. It measured ions, electrons, and cosmic rays from both the solar system and the galaxy beyond, providing the critical data that allowed scientists to determine precisely when Voyager 1 had crossed from the heliosphere into true interstellar space. Matt Hill, the principal investigator for the LECP instrument at the Johns Hopkins Applied Physics Laboratory, described its loss with quiet grief. He said that with the LECP, they had discovered properties and effects of cosmic rays and solar particles, and sensed the changes in the region around the spacecraft that determined when Voyager had crossed from the solar system into interstellar space. That instrument is now off. Each Voyager originally carried 10 sets of instruments, and 7 have already been turned off. Kareem Badruddin, Voyager mission manager at JPL, said that while shutting down a science instrument is not anybody's preference, it is the best option available. Voyager. One still has two remaining operating science instruments, one that listens to plasma waves and one that measures magnetic fields. Those two instruments, the Plasma Wave System and the magnetometer, are the ones that are still detecting the plasma hum, still measuring the magnetic field of interstellar space, still sending data back from a place no other human-made object has ever been. They are working great, but they require power, and the power is running out. The most remarkable and most closely watched development in the Voyager program heading into the second half of 2026 is a procedure that NASA engineers have given the deliberately dramatic nickname the Big Bang. The Big Bang is not what it sounds like. It is not a controlled explosion. It is an electrical engineering maneuver. Engineers at JPL believe they have identified a way to reconfigure the power distribution system inside Voyager 1 to free up a small but meaningful amount of additional electrical power. The specific details involve the voltage regulation system, a component that has been protecting the spacecraft's instruments from power fluctuations for nearly 5 decades, and that consumes a small, steady amount of electricity in doing so. By carefully reconfiguring how the power bus is managed, engineers believe they can recover enough watts to potentially reactivate the LECP and extend the operational life of the remaining instruments by approximately 1 year. The Big Bang will first be tested on Voyager 2, which has slightly more available power and is closer to Earth, making it a lower risk candidate. Tests are planned for May and June of 2026. If they go well, the team will attempt to implement the plan on Voyager 1 no sooner than July. The caution is appropriate. Voyager 1 is operating in a temperature environment near absolute zero. It has been running continuously for nearly 50 years on hardware that nobody has been able to physically inspect or repair since the moment it left the Earth. Every change to its operating configuration carries risk. The Big Bang maneuver involves modifying a system that has been running reliably for decades, and there is a real possibility that modifying it causes an unexpected failure. The engineers are making that choice anyway, because the alternative is a certainty. Without the power recovery, the remaining instruments will have to be shut down within the year regardless. Power margins have grown razor thin, requiring the team to conserve energy by shutting off heaters and instruments, while making sure the spacecraft does not get so cold that its fuel lines freeze. That last constraint is not theoretical. The propellant that Voyager 1 uses for its attitude, control thrusters, hydrazine, freezes at temperatures that the spacecraft could reach if too many of its heaters are turned off. If the fuel lines freeze, the spacecraft can no longer maintain its orientation. If it cannot maintain its orientation, its antenna can no longer be pointed at Earth. And if it can no longer point its antenna at Earth, the mission is over, permanently and irreversibly, regardless of how much other hardware is still functional. The engineers managing Voyager 1 are threading a needle between too much power conservation, which risks losing the spacecraft's thermal control, and not enough, which risks losing the power needed to keep the science instruments running. The IMAP mission, the Interstellar Mapping and Acceleration Probe launched in 2025, is the closest thing to a successor to Voyager's interstellar science. IMAP sits at Lagrange Point 1, about 1 million miles from Earth in the direction of the Sun, and uses far more sensitive modern instruments to study the outer heliosphere and its boundary with interstellar space through remote sensing. Scientists describe IMAP as IBEX on steroids, referring to the interstellar boundary explorer that preceded it. But IMAP is at Lagrange Point 1, not in interstellar space. It is reading the signals that come from the heliopause boundary from the inside, the same way you might press your ear against a wall to hear what is on the other side, rather than walking through the door. Voyager 1 and Voyager 2 are the only instruments that have walked through the door. They are the only probes that have ever been physically present in interstellar space. Every measurement they make is irreplaceable because no mission is currently planned to follow them. Getting another spacecraft to interstellar space would require decades of travel. Any mission launched today would not cross the heliopause until the 2040s or 2050s at the earliest. The data that Voyager 1's 2 remaining instruments are still collecting right now is data that humanity will not be able to collect again for at least a generation. The Voyager program began with a remarkable piece of cosmic luck. In the late 1970s, the outer planets of the solar system were arranged in a configuration that occurs only once every 175 years, a grand alignment that allowed a spacecraft to visit all 4 outer planets on a single trajectory using gravity assists from each planet to slingshot the probe to the next. NASA's Jet Propulsion Laboratory recognized the opportunity and designed 2 spacecraft specifically to take advantage of it. Voyager 1 visited Jupiter and Saturn. Voyager 2 visited all 4, making the only close flybys of Uranus and Neptune in history. The data those flybys produced remains the primary scientific basis for our understanding of the ice giant planets, and no follow-up? Mission to either world has yet been launched. The same missions that gave us the only close-up views of Uranus and Neptune also inadvertently set both spacecraft on trajectories that would carry them out of the solar system entirely. Nobody at launch explicitly planned for the interstellar phase of the mission. It was a gift that the grand alignment made possible as a side effect of the mission's original objectives. The golden records aboard both Voyager spacecraft have always been the most human dimension of the mission. Carl Sagan led the team that designed them. Each record is a 12-inch gold-plated copper disc carrying 115 images, a variety of natural sounds, music from different cultures and eras, and spoken greetings in 55 languages. They were included as a message to eventually encounter the spacecraft after it had traveled beyond our solar system. The odds of any alien civilization ever finding either Voyager are, to be honest, essentially zero given the scale of the galaxy and the speed of the spacecraft. But the act of including them says something important about the human beings who designed the mission. They were not just sending a scientific probe into the unknown, they were reaching out. They were saying, in the most enduring medium they could devise, that life exists here, that we think and feel and create, and that we were curious enough about what lay beyond our own cosmic neighborhood to build a machine and send it there. Voyager 1 will not last forever. The two instruments still running, the Plasma Wave Subsystem and the magnetometer, will eventually face the same power constraints that forced every other instrument to go dark. The most optimistic estimates suggest that Voyager 1 may remain in some kind of contact with Earth until the early 2030s, though that estimate depends on the success of the Big Bang maneuver and on engineering decisions that have not yet been made. By the 2030s, even if the spacecraft is still functioning, it may no longer have enough power to transmit data that the Deep Space Network can reliably detect. The mission will end not with a dramatic failure, but with a gradual fading, a signal getting fainter and fainter until the noise finally overwhelms the data and the universe goes quiet where Voyager once spoke. But what Voyager 1 has already told us about the plasma hum of interstellar space, about the moving and breathing boundary of our heliosphere, about the magnetic fields of the medium between stars, about the density variations and pressure fronts that structure the void between solar systems, has already changed our understanding of the environment beyond our own cosmic home in ways that will take decades to fully absorb. The deep space mystery that Voyager revealed is not a single shocking discovery with a simple explanation. It is the discovery that the universe beyond our solar system is more complex, more structured, and more surprising than any of the models built before any instrument had actually been there to look. In the fading final years of its power supply, with only 2 instruments still open to the night, Voyager 1 is still looking. And what it still finds matters more than ever.